This is the demo for section 3.3 for differential equations. Consider the linear system. We have x prime y prime is equal to the coefficient matrix -2, -2, -1, -3 times xy. Find the eigenvalues of the system by solving the characteristic polynomial. The determinant of a minus lambda I equals 0. So we're going to take the determinant of a minus lambda I. So that is going to be -2 minus lambda, -2, -1, -3 minus lambda. And then the determinant is a times d minus b times c. -2 minus lambda times -3 minus lambda minus -2 times -1. Simplifying, we get, I'm going to FOIL this out here, and I get 6 plus 2 lambda plus 3 lambda is plus 5 lambda plus lambda squared, and then minus 2. And combine like terms, we have lambda squared plus 5 lambda plus 4. That factors to lambda plus 4 times lambda plus 1. We finally set that equal to 0, and then that means you can set each factor to 0, and we get lambda equals -4 and -1. Those are our two eigenvalues for the system. Okay, next we want to compute the eigenvectors associated with each eigenvalue. That's a typo. By solving a times v equals lambda v. So a is -2, -2, -1, -3. V is an unknown vector, the eigenvector we're looking for, equals lambda, so we'll choose one of the lambdas, we'll do -4 first, times the same unknown vector, xy. We can translate this to a system of equations. So we have -2x minus 2y equals -4x. Now the second equation will either give you no information at all or the exact same information as the first equation. So if the first equation gives you enough information, that's the only one you need. So I want to solve this for y. So I have -2y equals -2x, adding 2x to both sides, which means y equals x. So any vector with an x and a y entry that satisfies y equals x, other than 0, 0, because 0, 0 never counts as an eigenvector, will be an eigenvector. So 1, 1 would be 1. So would 2, 2, or pi, pi. They're infinitely many. Then we do the same process for the other eigenvalue of -1. Okay, translate this to an equation. So we have -2x minus 2y equals -x. I'm going to solve for y, so I add 2x to both sides, and I have -2y equals x. So y equals -1/2 x, just divided both sides by -2. And then I'm going to choose any xy pair that makes that equation true. As a personal preference, I prefer to have whole numbers in here and not fractions. So I might choose x to be 2 so that my y value would be -1 and I don't have to deal with fractions. I chose the 2 so that it would cancel with the 2 in the denominator. So there are my eigenvectors. Just needed 1 for each eigenvalue. Okay, now we use each eigenvalue and associated eigenvector to write a solution of the form e to the lambda tv. So my first solution is going to be y1 is e to the -4t times the associated eigenvector 1, 1. And my second particular solution is going to be e to the -t times the associated eigenvector 2, -1. Now we check that the two solutions are linearly independent by evaluating y1 and y2 at 0 and showing that the two vectors are not multiples of each other. So y1 of 0, that is e to the negative 4 times 0 times 1, 1, which is 1, 1. And then y2 of 0 is e to the negative 0 times 2, negative 1, which is 2, negative 1. So those two vectors are not multiples of each other, so they are, in fact, linearly independent solutions. In general, when you have two distinct eigenvalues, two different eigenvalues, they will produce two linearly independent solutions. So after today, I won't have you check this linear independence. Okay, now we're going to use our two linearly independent solutions to write the general solution to the system. Okay, so my general solution is going to be y equals k1 times y1, and y1 was e to the negative 4t times 1, 1, plus k2 times y2, and y2 is e to the negative t times 2, negative 1. In the vector field drawn below, sketch the two straight line solutions we found earlier, as well as several other solutions to make a phase portrait. So the straight line solutions you sketch by putting in the eigenvectors associated with the eigenvalues and connect them to the point 0, 0, and then you make a line. So I'll do 1, 1. So here's 1, 1. Oops. Connect it to the origin, and that is one of the straight line solutions. It was associated with a negative eigenvalue, so the arrows point in towards the origin. And then my other straight line solution goes through 2, negative 1, and the origin. So about right here, we connect that to the origin. And that was also associated with a negative eigenvalue, so that points in towards the origin. And then we're going to draw in several additional solutions just by following the vector field. So these aren't going to be perfect. Just pick some initial conditions. Oops. Just pick some random initial conditions and follow the vector field into the origin in this case. So here's an initial condition. Follow the vectors to their landing spot. So I've got a few over here that all kind of swirl in towards the origin. And then it seems like over here they kind of do the same thing. Okay, then here's some kind of go like this. And it looks like if I had gone backwards in time, they would kind of come from there. And then these swirl in. Like that. So it kind of looks like a spider. So what we should notice is that most solutions that we drew here begin parallel to the eigenvector associated with the eigenvalue that is further from 0. So let's label these. This eigenvector was associated with lambda equals negative 4. And then this one was the one associated with lambda equals negative 1. So negative 4 is further from 0. So we see that the solutions start parallel to the eigenvector further from 0, and they end up swirling in tangent to the eigenvector that's closer to 0. This is generally true when you have two negative eigenvalues. This is a typical phase portrait whenever you have two negative eigenvalues. And when the solutions around the equilibrium point 0, 0 behave like this, we call this a sink. Every solution heads towards the origin. So like for this solution, for example, you can see it started out parallel to the eigenvector that has an eigenvalue further from 0 and ends up tangent to the eigenvector that has an eigenvalue closer to 0. Finally, we're going to find a particular solution that satisfies an initial condition, y of 0 equals 4, negative 5. And I wrote it horizontally. If you need to translate it when a problem is given like that, just write it down differently. Okay, so y of 0 would be k1 times 1, 1 plus k2 times 2, negative 1, because e to the 0 is always going to be 1, so those just sort of go away. And that's going to equal 4, negative 5. So translate this into two equations, the first component of each vector and the second component of each vector. So this says that k1 plus 2k2 equals 4, and k1 minus k2 equals negative 5. Okay, so you can solve this using your favorite method. If you took linear algebra, you can use this, do a matrix and row reduction by hand or on your calculator. If you didn't, then you would solve this by elimination or substitution. I think I will do elimination. So I'm going to put the second equation underneath the first, and I'm going to subtract the two equations. So k1 minus k1, those go away. Then I have 2k2 minus negative k2, which is 3k2, equals 4 minus negative 5, which is 9. So k2 equals 3. Then use either of your given equations to solve for k1. So k1 minus 3 equals negative 5. So k1 equals negative 2. So we have the values of k1 and k2. Now I can write down the solution. So the solution is this function, but I now know k1 and k2, so I'm just going to replace them. So y equals negative 2 e to the negative 4t times 1, 1 plus 3 e to the negative t times 2, negative 1.